Our second speaker for this session 2 is Dr. Sendil Rani. She is an associate professor in Department of Mathematical Sciences at ISR, Berhampur, Odisha. Her research interests lie in Fourier analysis and geometric measure theory, and her work focuses on Fourier asymptotics of fractal sets with applications to distance set problems and related configurations. Thank you very much for accepting our invitation and joining us. Over to you, Rani.
Hi, thanks for the introduction and for the invitation to have me give a talk in this session. I'm going to speak about quantitative existence of chains and sparse subsets of RD. So this is going to be like a two-part talk. First, I'm going to kind of give you highlights on how the results are going to be benefiting for the distance set problems, and slowly we will see what will be the analogous results on chains. So I'm going to start with all the basic notations. So for a given Borel set, I'm going to stick to the S-dimensional Hausdorff measure to be given by limit delta tending to 0 infimum of summation rj to the power s, E subset of union BRJ. So here BRJ can be any set of diameter RJ or ball of radius RJ. In my context, I'm also going to assume something called S-dimensional Hausdorff content, where instead of coverings for E via any open sets, we are going to stick to dyadic cubes. And in that context, both Hausdorff measure and Hausdorff content are going to be related to each other. Most importantly, if we have started with Borel set A, which is inside unit cube, then they are going to be much more comparable to each other. And hence, the concept of dimension is not going to change for the given set, whether we are going to speak about S-dimensional Hausdorff measure or S-dimensional Hausdorff content. So Hausdorff dimension of the given set is the critical point T for which whenever S is greater than T, the S-dimensional Hausdorff measure is 0, and S-dimensional Hausdorff measure of the set will be infinite for S less than T. So I'm going to stick to Ln to denote the n-dimensional Lebesgue measure, but I think rest of the notations I'll explain while we are talking during the slide. Another important basic property that I'll keep using here is the Frossman measure. So for a given set, as long as we have S-dimensional Hausdorff measure to be positive, we will have a Borel measure mu satisfying ball condition. Ball condition being mu of ball of radius r centered at x is going to be dominated always by r to the power s for all x and for all r greater than 0. And the Hausdorff dimension can be spoken in terms of these Frossman measures, and as well, all those measures that have finite energy condition. So what is finite energy conditions? Like you start with the energy integral, which is given by integrating the potentials at every point in the given set. Whenever we have this energy integral to be finite, we consider those collection of measures, and those are going to give the Hausdorff dimension as well. So this is one of the basic property that I'm going to assume multiple times. Another basic, like some of the basics that I'm going to assume the audience might know is that for a given function, the Fourier transform, for a given integrable function, the Fourier transform is going to be defined as f hat of z, integral f e power minus ix dot z dx. And this particular function is bounded as a Fourier transform of an L1 function is going to be bounded. Nevertheless, we cannot say the same when you're going to start with f belonging to LP for any other p other than 1. So over there, we usually discuss through the distributions. So in a general setup, if I have a compactly supported Borel finite measure, then we can define the Fourier transforms in terms of temper distribution, in the sense of temper distributions. However, because it's compactly supported through Pelley-Wiener theorem, we can say that mu hat is going to be real smooth. And hence, we can actually talk about pointwise Fourier transform for the given compactly supported finite measure. So given a compactly supported Borel finite measure, then the energy integral using some of the analog of Parseval's proof, we can say that IS mu, that is the energy integral, can be written in terms of frequency setup as well, not just the spatial. Okay, let's step into the definitions that we need for this talk. So I'm going to assume in fact, I'm going to start with Borel sets, which are going to be inside unit cubes. And for the given set inside the unit cube, I will start with the distance set to be the collection of all distances, which is mod of x minus y for x and y belonging to E. So very trivial examples one can observe is when we start with finite point sets, then the delta of E, the distance set of E is going to be the same distance points, which is 0 to 1 n. And if I'm going to start with 0, 1, then it's going to be again the same 0, 1 interval. Whereas if I'm going to start with a unit cube, then it's going to be giving me the intervals, which is going to cover the distances as in the diameter of the given set, which is root 2. So distance set of Cantor set, on the other hand, is a very computative example one can do to figure out that the C plus C is basically 0, 2, which will eventually say that the distance set of the Cantor set is going to be 0, 1. In fact, we have seen quite a lot of examples in the first talk of today's session by Professor Simon, who had actually talked about self-similar sets with non-interior distances. So one of the construction that one can picture out even in higher dimension is very porous Cantor set. Like for very porous Cantor set, we will be eventually having the distance set not having any intervals nearby 0. Like Cantor set's distance set was actually near 0. In fact, it was 0, 1. However, we can construct Cantor sets which are very porous enough so that the intervals, the interval distances are not nearby 0, but of course it might have interval distances say nearby 1 when if you consider the porous set to be inside the unit cube. So this brings back to a lot of questions like how we can actually analyze the distance sets. Before going to the further questions, I would also like to recollect the definition of a K-chain that I'm going to stick to. So it's going to be an extension of the distance set, whereas here it's going to be K-chain, which means it's literally a chain. So I'm going to consider a sequence of points in which each of the points are connected. We are going to collect all of those distances of those three and call it as the K-tuple, and that K-tuple is my K distance set of E or K chain distance set of E. So one of the very trivial example, if I'm going to start with a finite point set 0, 1, n, then the K chain distance is going to be precisely the K tuple of 0, 1, n. However, this boils down to one another question. So our K chain distance set always going to be K tuple of the distance set? And the answer is no. Again, a very trivial example one can start with is the unit circle. So for the unit circle, we will have the distance set to be 0, 2 because you're having the radius to be 1 and hence the diameter is 2. So the distance will be varying from 0 to 2. Whereas if I'm going to talk about, say, even a 2 chain, which means like I need 3 points on the sphere such that each of these 2 points should have equal 1. But that's not going to be possible because the moment I'm going to stick to one distance, it's going to be a diameter. So I cannot draw another diameter without compromising the fact that x1 should be equal to x3, which is not what we want. We want distinct points. Because of this, we at least know that 2, 2 is not inside the 2 chain ones. And you can ask similar questions for 3 chains and so on. So here we do not have any restrictions on K chains because K can be anything greater than or equal to 1 for us. It is not going to be restrictive on the given ambient dimension. Okay, so this boils down to a few questions that we would like to answer. For a given set, So what can you say about the distance set? Can we talk about the Lebesgue measure of the given distance set? Can we talk about interior of the given distance set? If we can speak about interior of the given set, does it mean that we will be able to have one interval or two intervals or multiple intervals? Will we be able to actually point out what sort of intervals will be inside the given distance set? All of these questions can be asked when it comes to sets in RD. So for D equal to 1, the questions are a bit different. And of course, as Professor Simon said, there are a lot of open questions even to answer for D equal to 1. So we will not be focusing on D equal to 1 case in this particular talk, and we will be focusing on D greater than or equal to 2. Leisurely, it's because for D greater than or equal to 2, we have nice configuration integrals. I'll soon come to what do I mean by configuration integral. Now, if I have those results, whatever the questions that I asked about interval distances, be it existence or quantifications, will we be able to extend all of those results for generic K-chain sets? So we saw that it's not going to be simply a K tuple of the distance set. So that kind of like boils down to questioning whether we will be having the same techniques or different techniques, analytical techniques, in order to prove the existence and the quantifications of the existence. First, I'm going to focus on existence part because my question was quantitative existence of chains. So I'm going to first draw analogous results from existence of interval distances with respect to the interval K chains, and then I'm going to shift to the quantitative results. Okay, let's start with the famous conjecture that if I'm going to give you a set E, and if I have the dimension of the given set to be greater than n over 2, then the Lebesgue measure of the distance set is going to be positive. So this is the conjecture that was coined by Falconer. Of course, I'm going to assume n to be greater than or equal to 2. So Falconer actually observed an example which was straightforward to say why that exponent of n over 2 was in picture for us. So heuristically, you can start with the lattice, which is like you can consider all the lattice points in the unit cube with respect to as large n as possible that you can think of. And if we are going to just count all of these distances between these lattice points, that's going to give us a number. And thankfully, number theory, it's been already kind of like another set of results that describes how delta of En is going to behave. And that over here, it's behaving as n over root log n. And this clearly says that it's not precisely n. Like En's, the cardinality is n, whereas the distance set of En is kind of like way away from n. So as n tends to infinity, we can see that En is becoming very dense in 0, 1 square. And that's kind of like contributing some information on how distance set is prevailing. So this one information on how, the structure of En or the denseness of En is playing a role is vital for us to kind of like coin the conjecture. And Falconer actually proved the same thing by having so large n with respect to appropriate exponents of n for, and kind of like put all sorts of lattice cubes over there and then start constructing Cantor kind of sets. And this set was giving you a set of dimension s for less than or equal to n over 2, whereas the dimension of the distance set was also closely behaving like an s. And definitely, the Lebesgue measure is 0 for that distance set. So this this is not a heuristic example, at least the heuristic behavior that we have discussed before is giving us the exponent n over 2. Now, on the other hand, what we are actually asking is not just about, the Lebesgue measure of the distance set, when can we actually ask about interior of the distance set. So at least immediately, like Falconer answered that when we have the dimension to be greater than n plus 1 over 2, then we have a big measure of the distance set to be positive. So In fact, like Metila gave much more better proof for this on how the interior of the delta A is going to be non-empty. So we will briefly revise, like how the proof is done, because that's going to play a vital role in understanding how analogously we are going to build tools, and the proof is going to be different for chain and distances. Okay, so how do we do this? Like we start with a Frostman measure on the given set A. Since the given set is of dimension greater than d plus 1 by 2, we are safe to assume the Frostman measure having a ball condition of r to the power s, where s is greater than d plus 1 by 2. With respect to this measure mu, then we are going to cook up a measure on the distance set. So this distance set measure is usually is a convolution with respect to the spherical measure. And through that spherical measure, we build another, like measure on the distance set. So here is the nice trick. We are going to use Fourier analysis over here to say that this particular mu that we have obtained on the distance set is going to be absolutely continuous. So how do we do that? We have a nice structure on how the Fourier transform of the mu is going to behave, not just the Frostman measure on A, but the measure on the distance set. We are able to approximate it via the Fourier transform, and we are able to actually come up with a Fourier decay of like average Fourier decay with respect to the spherical measure uh, to behave like r to the power minus n minus s. And because this is going to behave like r to the power minus n minus s, we have this whole estimate to be this. And so you can clearly see that this estimate is going to be finite only when s is greater than n plus 1 by 2. So that boils down to saying that nu hat actually is an L2, which means nu is also an L2 function, and hence it's absolutely continuous. Using Plancherel's theorem, we are able to say that nu is absolutely continuous. So this concludes that we have a measure which is absolutely continuous with respect to the Lebesgue measure on the distance set delta of A. And hence, I'll be able to say that the Lebesgue measure of the distance set is positive. So this is a neat trick to just say that the Lebesgue measure of this is positive. Whereas if we have to say the interior is non-empty, we go back to the configuration integral over here. We are going to pin in the sigma t, which means we are going to specify the t distances in the configuration integral. And from there, we are going to say this configuration integral itself is continuous, and that is going to give us the non-empty interior. So that's Metalas proof. So I'm not going to the details of Metalas proof over this slide. But this basic setup is going to help us out for proving the rest of the results. Okay, so if I'm able to say the existence, so this clearly gives you the existence. So how can I actually now improve these results to say that existence of k-chain intervals is? So what do I mean by that? Like we had the distance, like we had an analogous definition of distance sets for k-chains, which is delta k. So can I ask whether that is going to have some sort of Cartesian products of intervals inside this particular k-chain distances? So the question is similar, while the basic intuition behind proving this is also going to be similar, which means we will have to come up with a configuration integral. However, like in order to prove that the configuration integral is giving us a non-empty interior is going to be a bit different. So how do we actually start with the configuration integral over here? So just like how we started with distance set, here we will be having iteratively many, because we are actually considering say x1 minus x2, and from x2 I should have another x3, and hence we have to have an iterated integration over here. So suppose I start with rho epsilon to be a suitable approximate identity. And if I'm going to consider all those points xi plus 1, which are going to be of distances ti. So I'm going to fix, for convenience sake, we can assume t to be equal to t comma t comma t, which means like all the k-chains are of equidistance. So we are collecting all of those points at t distance for each of the vertices. And with respect to this iterated integration, then we will have a Frossman measure mu to be on each of the sets. So if I'm going to blindly follow what we had do it for the distance set, we have to start with mu to be a Frossman measure on the given set E. And with respect to that, we are going to have an iterated integration. Now, the challenge is, unlike the distance set configuration integral, whether this configuration integral is going to give you a neat frequency site analog integral. So the answer is no. So this is where the technique kind of like is different. And this was actually proved by Bennett, Eiswich, and Tyler in 2015 of breaking this integral with respect to the operator integrals and dealing with each of the operator integrals. So let me explain a little bit more of what they're doing over here. So recall that this CK epsilon, the configuration integral, is epsilon thickness set. So if we want it exactly on E, we need to ensure that as epsilon goes to 0, the CK epsilon is going to a particular configuration integral, existing configuration integral. That's catch number one. Second one is that this particular configuration integral itself is having iterated integrals. So what we are going to do, we are going to build up a tool for each of these iterations. So let me start with a config, like one of the innermost integral to be TT epsilon. And then we are going to slowly compose it with the other TT epsilon so that we can build the iterated configuration integrals. So notation wise, TT epsilon is going to be this. And then, like we are building the composition over here, call it FK epsilon. So then CK epsilon is literally integral FK epsilon over d mu. So how do we do that? So we are going to actually figure out for each of the TT epsilons and see if we can actually bound it so that I can talk about CK epsilon's existence as epsilon tending to 0. So that's our first part. So the first part is going to be pretty easy in some sense because we can still use Fourier analysis to break into Fourier side of integral. Like we can, dominate the given each of the pieces, iterated pieces, to dominate it above by F mu hat. So this, since you have mu to be a Frossman measure, it has finite energy integral, and that is also going to help us out say that this F mu hat mod square mod zeta to the power minus t minus 1 is going to be dominated above by L2 norm of F. So we will be using the Frossman measure condition to say that this is actually dominated above by L2 mu. However, with one condition that S definitely has to be greater than t plus 1 by 2. Since you can see that this is going to be finite only for S-dimensional measures, Frossman measures for S greater than t plus 1 by 2. So with that bounds on each of the integration that we have, we can keep plugging it inside of this original integration, that CK epsilon that we have, to finally conclude that this is going to be dominated above by 1. Now, this actually says that CK epsilon as epsilon goes to 0 is going to be finite. So at least lim sup epsilon going to 0 is existing. So we are in a good shape to talk about the configuration integral. So existence of configuration integral is what we have discussed so far. And we haven't actually yet said how this is going to be actually, giving the existence of K-chains. Unlike distance set, where we actually had the configuration integral to be continuous, over here, in order to prove that continuity, we will have to prove that lambda k of t, which is the limiting argument of the CK epsilon, not only exists but also continuous. So again, the continuity argument is fairly simple. It's just metric spaces that, like basic metric spaces theory, will tell you that this is continuous. However, to prove that it exists, which means it's non-zero, is kind of a challenging one for us. So that is the entire paper is all about, in proving, that lambda k of t is bounded away from 0. Because that is going to tell you that, yes, this configuration integral is supported inside delta k of E, and hence, delta k of E is non-empty. And moreover, we will also have to say that it's continuous with respect to t, so that like not just, like one point we have, because of the continuity, we have definitely a point and its neighborhood, which is going to be sitting inside the k distance set. So here, when I say neighborhood around t, I'm going to talk about neighborhood around k tuple t. So we are in k space over there when we are speaking about the continuity over there. Okay. So I don't think I have enough time to actually get into the proof because it's highly technical, and hence I'm going to skip the proof of how this lambda k of t is non-zero. So assuming that we have proved that it is non-zero and hence the existence of k chain is done, I'm going to move on to the next topic that we are going to discuss, which is quantitative estimates. So not just that we are proving existence of the given set, we are trying to prove quantitative, which means not only that the continuity is enough, we would like to pinpoint for what t we will be able to say that the configuration integral is going to be positive and finite, not just in distance set, but also in k-chain. So first, I'm going to highlight the results that we have for distance set, for where how this t is obtained, like how this interval is obtained. So I'm going to go a little bit detail in proving this quantitative estimates so that you can see the analog, and later I'm just going to wrap up with the theorems on the k-chain, hinting about the proof techniques for k-chains. Okay. So the question that we are asking is not so, new. It started even in 1920 and 1942 of starting with a given set. As long as you have the Lebesgue measure to be positive, can we say that there will be an interval inside? In fact, it was positively answered, and the proof is very simple by using basic measure theory to say that there exists a C such that 0, C is going to be inside the distance set. Now, we know that this C that we have obtained in this particular result will depend on E. So the question now comes, the later part of, question comes about of, can you say it in general? Like, can you say it in generic aspect? So that's what Boardman actually answered in 1970, that you give me a class of sets for which the Lebesgue measure is definitely going to be greater than or equal to 1 minus rho, then I'll definitely find you 1, 0, now no longer depending on E, but only depending on the content of E, which is 1 minus rho. So I'll be able to find out an endpoint such that 0, 0 is 0 root D is going to be sitting inside distance set of E. And we can see that this half, that rho less than half, is an optimal estimate when D equal to 1. Unfortunately, it is still open for D greater than or equal to 2. Since that, like, we are discussing only results on D greater than or equal to 2, I do not know what even is the optimal point for rho. So we can definitely construct something called a rho, like we can construct at least until some point like 1 over 2 to the power d by 2, but I'm not sure can we go rho till 1 over 2. That is still unclear when it comes to the optimality. Okay, so this is kind of a quantitative estimates for Steinhaus. So combining what we had seen earlier and what we are currently seeing, I would like to draw an analog. So the previous results that we have seen so far was just answering, like on one particular E. So what we are right now doing is quantitatively, we are going to explain that it doesn't matter what sort of E you have, as long as it has Hausdorff content or the Lebesgue content to be greater than or equal to some positive number, of course, closer to 1, I'll be able to tell you what sort of interval is sitting inside. So that's the question that we are heading towards. Now, when it comes to, questions, analog questions of Steinhaus or Boardman's result for Hausdorff sets, as in like for thin sets. Say, for example, if I start with E to be in RD such that the Hausdorff dimension of that particular set is very close to D, we will definitely assume greater than D plus 1 by 2 because, like the existence has been proved only for greater than D plus 1 by 2. So I can assume dimension to be definitely greater than D plus 1 by 2. And in fact, we will assume to be very closer to D. So the question is, can we still find an interval of the form 0, comma c sitting inside the distance set of E? So the answer is no, that's what I started with, the porous sets. You can construct extremely porous sets in which the delta of E, the distance set of E, will not have an interval around 0. But however, we are able to prove that as long as the Hausdorff content is closer to 1 and the dimension is closer to D, we will definitely find some interval in delta of E, but not necessarily around 0. So that's the first result that we are going to see in this talk. So you give me a D, I will find you a row such that I can find a very small number A, B, and a row, which is going to be, and an epsilon, which all of these constants are going to be depending on the row that I had started with, such that whenever you give me a Borel set of dimension closer to D, which means S is actually greater than or equal to D minus epsilon rho, so which is very close to D because epsilon rho for me will be very, very, very small. And the Hausdorff content is also going to be very closer to 1 because the row that I have started is also small. Then A row comma B row is going to be sitting inside the delta of E. So we will be able to pinpoint what this A row and B row in terms of row, like something like row to the bar for a very small kappa, say row to the bar kappa times log row. That, like, I'm kind of like being vague here, but we do have a very precise estimate of A row and a B row in terms of row. So there exists a RODI, and in fact, this RODI is also kind of like can be specified explicitly as long as it's very closer to, say, 1 over 8 for D equal to 2. It works. So on that basis, now that I've explained the sentence, we can actually go about how the proof is done. Because you see that the only assumption that we have here is that the set has Hausdorff content close to 1. So the rest of the assumptions that we have on the dimension or on the content closer to 1 is all depending on the variable that we had started with. So how is this, like building out A row and B row? It is not spatial structure at all. So we will see how the frequency is coming in hand. Like Fourier analysis is coming very helpful in order to actually cook up this A row and B row. So quantitatively, although you can do some of the results that we had discussed previously without Fourier analysis, like just directly going about spatial structures, over here, we definitely need the Fourier analysis for us to help us out, but not directly as Fourier transform of the measure, like how we saw, like in the previous talk. We are not actually going to talk about Fourier decay or polynomial Fourier decay over here. Instead, we will be talking about the spectral gap that the previous speaker was talking about. Okay, let's break down the proof. So the first thing that we want is the configuration integral. So I'm going to write it in terms of convolution, but it's the same thing that we had seen when we were talking about Falconer's proof and Metalas proof. I'm going to thicken the set so that like I can talk about the existence, and then we are going to talk about this lambda t being non-zero. So that's the vital part, because like I have discussed in detail of how this is going to be finite even in K chains. So proving that this is going to be positive is what we would like to focus on in this proof. Nevertheless, compared to the first proof that we have seen by Falconer, the Frossman measure is no longer going to be helpful. Like I cannot just start with any Frossman measure on the given set, because that's not going to give us any results on the Fourier analytic aspects. So what we are going to do is carefully build this measure. So this finer analysis of this measure is basically that it's spread it out everywhere. So because we had assumed that the Hausdorff content of the given set is closer to 1, it's kind of like well distributed inside the unit cube itself. So because of this well distribution, we will be able to find out measure on the well distributed sets inside. So I'm going to consider a dyadic decomposition of this unit cube, and through this host of content, we will be able to finalize the level of the dyadic cube that I can go until where I can figure out that each of the cube will give me a Frossman measure. So here when I'm writing it out as spread it out, and when I'm mentioning that mu is made of sum of weighted Frossman measures on each dyadic cube of the unit cube, this cube is going to be obtained through the informations that we have for the host of content. So the host of content, which is like greater than or equal to 1 minus rho, that's going to play a very vital role in discussing the length of this cube. So once we have that information, we will spread it out and then build off this mu. And we will definitely need to include weight on these measures. And this mu q that I'm going to talk about is the usual Frossman measure on that dyadic cube, each of the dyadic cubes. And I'm going to assume it to be a probability measure. Okay, so since we are building up with the same Frossman measure, like all the mu q's on each of the q is the same as Frossman measure. So because of that, it's kind of like straightforward for us to see that the dimension e greater than or equal to s will be also obtained through this measure, and the finite energy condition will be satisfied. So how are we going to assume this WQ? So the mu Q is playing a vital role in satisfying the condition of an finite energy integral. And also, like how it is of dimension greater than or equal to S, the dimension of the measure greater than or equal to S. But what's the role of the WQ that I mentioned? Why do we introduce this weight? And what's the role of this weight for each of this Q? So that weight is precisely going to be integral over Q of phi, where phi is going to be a very nice smooth function for me. However, this phi will have nice Fourier decay. So this is where, like the Fourier decay is kind of like sneaking in, because I cannot afford to think of a measure mu, such that the Fourier transform of this measure mu is having a nice decay. In fact, even if we are going to assume Selene sets, say where you have the measure mu having appropriate Fourier decay, that still was not giving us the quantitative estimates of the distances. So directly asking for the Fourier decay of the measure mu to be supported on the given set is not directly helping us out. So we need to, tweak out this measure mu and kind of like think about some sort of a decomposed push forward measure whose Fourier transform is behaving nicely. So what we do is, so that's the weight we are adding over here. So here, if I'm going to assume phi to be a very nice smooth function supported on the unit cube, such that the Fourier transform of the phi is going to be decaying as much as I want, that integral q phi is my weight of q. So that is going to give me the spectral gap of mu hat. So integral mod of mu hat over the annulus, like we will be able to figure out this A and B precisely coming from the Q that we have started. So how you started with a row, that row is giving me this T, and this T is giving me this A and B. So in particular, A and B is directly depending on the row that you have started with. So that A and B is the annulus that we have, like since A and B are very small, we have this annulus very, like far away from zero. And the thickness is also kind of like pretty big. So during this particular frequency annulus, we have the mu hat behaving very small. And of course, it'll blow up afterwards because, like the mu that we have started was any measure on the given set E, and we not necessarily are expecting the given set to be of, Fourier dimension to be greater than zero. So we do not know that. So of course, this mu hat will behave very badly as zeta tends to infinity, whereas what we are claiming is like there will be a middle annulus region where this mu hat is behaving very nicely. So this gives us the spectral gap that's needed. And this particular spectral gap that we have obtained is also giving us explicit distances. That is, this B inverse and A inverse is what giving me the distance A comma B to be interval distance A comma B sitting inside delta of E. So recall that this lambda T is basically the limiting argument of this configuration integral. So we have to actually prove that lambda t is bounded below and above by a fixed constant. So how is this, spectral gap, coming into picture at all to prove that this is bounded above by a fixed constant? Bounded above by a fixed constant is easy to prove, which we have seen in the K-chain existence. So my question is how lambda t is bounded below by a fixed constant using the spectral gap condition, using the construction of mu that we have. So the answer is going to be another step-by-step, decompositions of the proof. That is that you give me the configuration integral. I'm going to break into three pieces. First of all and foremost, the existence is already done. That is lambda t is, this limit as epsilon goes to 0 exists, and hence lambda t is existing. And we have the liberty to kind of like write this lambda t in terms of the frequency variables because we are still in distance setup. So lambda t can be written in terms of frequency setup, which is going to be integral of, so this is my integrand for lambda t over all psi. So that will be my lambda t. So I'm going to break this into three regime. One is low frequency, another is middle frequency, and the third one is the higher frequency. So since, like we freshly finished what is middle frequency, as in what is the spectral gap, I'm going to give a pause and first start with middle frequency region. So note that this middle frequency region, so how we have actually decomposed this integral is, you can see that this t is my t distances. So let's go a little bit slower here. Integral sigma t convolved with mu epsilon is going to be integral mu epsilon x minus y minus t omega t sigma of omega t mu epsilon. So what you have, you're collecting all those pairs x comma y such that mod x minus y is going to be behaving like a t. So t is my given distance. With respect to that t, we have this configuration integral. I can switch over the frequency side over here, and I'm going to break this frequency with respect to the t that we have started with. So whenever mod zeta is less than or equal to delta t inverse, we can see how sigma hat of t zeta is going to behave. And then for delta T inverse to delta inverse T inverse, since I said that the middle spectrum, that this particular spectral gap is applicable for B inverse and A inverse, whenever I start with T belongs to A comma B, T is going to be less than B and T is going to be greater than A. So I will be able to dominate this above by this particular spectral gap. Why? Because sigma hat of t xi is going to be bounded above by 1. So this modulus of this middle spectrum, the middle frequency region, is going to be dominated above by a square, where a is very small. So that takes care of this to be an error. So you would think that this is giving us the distances, and hence this is going to give me the lower bound, and unfortunately that's not the case. Higher frequency, on the other hand, as well is going to be an error for us because here we are going to carefully use the Fourier decay of sigma hat because sigma is my surface measure, normalized surface measure on the sphere. I have pointwise Fourier decay for sigma hat. So this is going to bring back t to the power n mod zeta to the power minus t minus 1 by 2. And we clearly have stated that the constructed mu is also going to satisfy energy condition for us. So because it is going to satisfy the energy condition in the frequency variable setup as well, this now can be dominated above by a very smaller quantity as long as t is in a comma b. Over here, we will be using t belonging to a comma b, where the lower bound of t is going to work out. So, lower bound of t will work out. So having said that, so these two are going to be contributed as error, which means mod of this middle frequency is also dominated above by a squared, which is a very small term, and higher frequency is also going to be dominated above by a to the power something. So both middle frequency and higher frequency are my error, which means the lower frequency is going to contribute the lower bound that we require for lambda t. So how do we prove that? Again, that's kind of straightforward if you have already seen these techniques. Sigma hat of t xi is basically nothing but, the surface like sigma is basically the surface measure. So I'm going to use the spatial structure of the sigma instead of the frequency setup. And using the spatial structure of this, I can dominate this by below half of integral mod mu hat to the power 2 dz. Now, if you have already seen some Fourier asymptotics or L2 Fourier asymptotics, you will cleverly see that that's a very big integral. It will definitely be bounded below by a very big quantity if you are going to say, for example, assume Alphonse-David regular sets. Since again, we do not know whether the constructed measure is Alphonse-David regular measure, and it's highly possible that the original set that was given is also not Alphonse-David regular set. So the dominating term for this particular low frequency, we are going to obtain it directly through the spatial structure of this mu. So we will just use the fact that mu is a probability measure. And since it's already dominated below by a positive integral on mod zeta less than or equal to delta t inverse, I'm going to carefully choose this delta to be, say, very close to 1 by 2, so that this mod zeta less than or equal to delta t inverse, I would also choose, t to be inside a comma b, where b is less than delta. So using those, observation, we can dominate this below by integral mod zeta less than or equal to some fixed constant. Like that constant can be, say, 1 by 2 to the power 100. So that will, along with the property that mu is probability measure, will give us the lower bound, which is going to be only depending on d, and it is not going to be depending on the mu or the delta, like because I'm going to assume delta to be 1 by 2. Okay, so since this is going to be dominated below by a fixed constant, say omega d, and the rest of the things are chosen to be smaller than a, that is where the first assumption on a comes in handy. Because I have chosen already a with respect to the row, and since this a has to be smaller than the omega d that we have obtained through the low frequency region, that pushes us how this a is going to be chosen. And that is going to push us as again how the row is going to be chosen. And that row is what, we have it in the first hypothesis. So, well, this is the finer analysis that I can actually explain over here. So having said that, now I will briefly recall the results on K-chains. So this is an ongoing work, which means like we are, trying to do the quantifying statements on not just chains, but we have also obtained it on trees in general, and we have, to some extent, have come up with some other patterns as well. And we are closely working on examples to kind of like see how, like this intrinsic detail is playing a vital role, or, makes sense to talk about quantitative estimates. So the technique is not going to be simply like what we have done in distance sets. Like in the distance set, we kind of like split it into 3 integrals, and that was working like a charm for us because we had this Fourier decay property of sigma hat and we had this spectral gap of mu hat. That was kind of like coming in handy to come up with this. However, for chains, the configuration integral that we have to work with is iterated integration. So because of this iterated integration, like the low frequency part, which, directly we can split it in spatial setup instead of going to frequency setup. Most importantly, we cannot actually write this in terms of frequency variable, unlike the distance set case. So what do? We split this lambda t epsilons. So this alpha for me is something like a k tuple of epsilon 1, epsilon 2, epsilon case, like that epsilons is my alpha here. So I'm going to break this lambda t epsilon, which is ck epsilon, which I have written in the previous slides, into smaller, spatial setup and then the error setup. And now here comes, the charm of Bennett-Iosevich-Taylor's proof. So that proof is going to highlight of how we can deal with this in terms of, again, middle frequency and higher frequency. And then we are going to use our construction and distance set problem to actually build the tools for dealing with each of the summand pieces to say that they are actually smaller at every L level over here in the summands. And hence, this is altogether is going to be very small. So we break this into smaller cases, like because of the iterations, you will kind of like break this integration into iterated integrations. And each of the summand for us is going to contribute a smaller term. We will just use, the same measure that we have constructed in Pramanic's Rani paper, uh, the advances paper, and we will be dealing with the lower bound for lambda t epsilon L through just by spatial means. So we will just use Vitali's theorem to bound it below by, uh, to have this measure to be bounded below by, say, r power d for some positive set of measures, positive measure sets. And through that, we will get the lower bound for this, and we will get the error term for this, combining both Yosevich method and Pramanic's method. I think I'm done with the proof strategy over here. So I don't think I'll be able to explain more technicalities other than this. Thank you.
Thank you, Rani. Let me close the recording.